So the first speaker is Ken Duncan, talking about the role of machine learning in radio continuum theory.
Thank you. Thanks for the invitation. So yeah, really I'm here presenting not my own work, but mostly the work of a master's student who worked with me in Leiden, Raphael Mostert, and I think he might be watching online, so hello. And also, this is also based on a lot of work by a huge amount of people within the wider LOFAR surveys team, and I'll kind of introduce that in a sec. So I just wanted to start with kind of my perspective on what's driving the rise in machine learning and astronomy, kind of why we're here. And I think the key conclusion, and we've seen it earlier, is that really we want to make science with very large data sets tractable. And this can come in many forms, and we've seen some of these already. Automate previously manual tasks that are very repetitive and time-consuming, do them with a computer instead. Speed up or improve key measurements that are required for large samples, so with the supernova classifications or things like photometric redshifts for these lensing surveys, for these, the cosmological surveys. But also we saw a little bit with Jim, we want to enable exploration and discovery of massive, within massive and complicated data sets. So I'm coming at this from the point of view of the LOFAR radio continuum surveys. So LOFAR is a radio survey or radio telescope that now spans the majority of Europe, extending from Ireland in the west to a new station being built in Latvia in the east, and a new one being built down in Italy in the south. And you can see this is the Super-Turp, which is at the very core of the observatory, and each of these little kind of black areas is the HBA part of the LOFAR. And underneath each of these, you can see these little dipoles down here. And the results I'm going to talk about today were actually based primarily on results from just the LOFAR core stations, which gives you about 6 arc-second resolution. If you add everything else from the international stations, you get down to sub-arc-second resolution. And obviously, at radio wavelengths, that's excellent and allows you to do a lot of very interesting science. LOFAR as a telescope is being used to do a great number of things. So this ranges from studies of the EOI, looking at 21 centimetre emission, deep extra-Arctic surveys, but also cosmic magnetism, transient, high-energy cosmic rays, but also looking at solar science and space weather, particularly because the radio waves we see in low frequency are very sensitive to the ionosphere. So we can do a lot about understanding basically how the sun works and also how Earth's kind of wider environment acts. So I'm obviously involved in the deep extra-Arctic surveys. And the plan is to do a northern hemisphere survey, and you can see how this is progressing in this kind of status, which is as of this morning. All the kind of broader circles are observations that have been taken, and the green ones have been reduced already. So you can see it's progressing pretty rapidly. But our initial data release, which came out last month, it was the tail end of February in an ANA special issue, is this LOFAR Two-metre sky survey DR1 HET-DEX Springfield. So this is kind of patch of the sky that will eventually be covered by the HET-DEX, the Hobby Dark Energy Experiment Lyman Alpha emission survey. So should have lots of ancillary data, but we're there first. So this is still a relatively small patch of the sky compared to the northern hemisphere, but the sensitivity LOFAR reaches, which is 70 microdioceses per beam, it's 320,000 radio sources in this small patch of sky, and that's about a factor of 10 deeper than existing all-sky surveys. So obviously, compared to the billions of sources we were talking about earlier with Euclid, these aren't huge numbers, but in terms of radio analysis, these are still pretty big numbers. It presents their own kind of unique challenges. So if you're interested, there's 3 main release papers that came out in the ANA issue 2 weeks ago. Tim Shimwell's paper on the radio images and catalogues, Wendy Williams' paper on the optical IDs to match these to the host galaxies, and then my paper doing photometric redshifts using a kind of machine learning plus template fitting technique, but I won't go into today. That's also there. There's also about 20 other science papers covering a huge range of things. And with the press release last week, or 2 weeks ago, we had a very exciting, I'm going to show this off, basically forever. So it turns out Chris Evans, the Hollywood actor and Captain America himself, absolutely loves our radio survey. And this is him retweeting directly the LOFAR press release. It's not even like from CNN or somewhere else that picked it up. He's directly from the LOFAR press release. So that's, I think, 15 million followers. And that's my outreach sorted for the next few years. But I think it illustrates kind of pretty cool, and actually sometimes why it's worth doing these press releases, because it does build the public engagement. And actually it was rewarding because this has taken a lot of effort by hundreds of people over the years. Anyway, so the scientific challenges. So LOFAR's depth, and especially its sensitivity to extended emission compared to previous all-sky surveys, presents an unprecedented zoo of new radio morphologies. And this is just an illustrative example of some of the interesting ones. And they're kind of vaguely recognizable as some of the classic radio morphologies, but we're in a new regime and there's lots of new features and there's actually things we've not seen before coming up in these samples. So how do we begin to explore and classify this new diversity of morphologies in a kind of unbiased way without having to refer to our previous sort of 50-year-old classifications? So going back to self-organized maps here, which Jim nicely introduced earlier, and I've added a nice little video to illustrate kind of the process. So as he showed, you take some input vector, which in this case is the MNIST handwritten characters, or you're mapping it to nodes on this self-organized map to find the one that's most similar, and then updating those nodes around it to kind of build the map up, and you rinse and repeat until you get to the very end of this exercise. And obviously, this is a bit of an artificial example because we know there's discrete classifications and numbers, but you can see that by the end, you sort of get what you're looking for. You've got zeros over here, ones over here. You've got the kind of bit of degeneracy between 8s and 2s and similar looking numbers. It's doing kind of what we expect. But this is for things that have specific orientations. And obviously, when we go to the radio sky, we don't really care about direction. And these jets can have any angle and any orientation. One way to look at it is the way that Jim's group approached it, is you can look at these in kind of different features, so Fourier transforms, or look at features themselves. The other way to do it is actually just to go brute force. So we've got GPUs now, so rather than comparing one cutout, we can rotate it and flip it. So we have our radio source at basically 360 degrees, and we can compare all those versions of the cutout to the self-organized map to find the best match at the best angle, and then update it in that way. And obviously, the prototypes that you build in the SOM have a particular direction, but you can actually fix those initially by just putting in a prior. But also, you don't really care about those directions. So we're doing this using a code that was developed by Kai Poster in Heidelberg. And it's called Pink, and it's fully GPU, so it basically means we can do it in this brute force way without wasting too much of our time. So following the same kind of process, we're taking all these cutouts from FITS files, so these are from the original radio images. We've run a source extraction to find our sources, turning them into input vectors, and then training our SOM. And this is kind of key in that people have seen this before, I mentioned it earlier, is that you're kind of pre-processing your assumptions make a big difference on what the end result is. So this is things like, for these cutouts, linear versus some sort of async or log stretch to accentuate or hide different features, sigma clipping to get rid of noisy regions, which can sort of dim your sensitivity to low surface brightness, but also, the shape of the SOM and whether you have it kind of, whether there are boundaries or you have it looping, but also things like the neighborhood function, etc. So when you run 15,000 extended morphologies from the LOFAR DR1 through this pipeline, you get this nice 8x8 SOM. It's an illustration. You can sort of see you've got doubles down here, singles, and other sources around here. But the reason I wanted to be special and have my own laptop is to show that once you have these SOMs, they're not just a way of kind of classifying data, they're also a way of exploring the data. So that SOM, this is a slightly bigger one. You can see you have some of the same features. So if you look over here, you can choose a particular prototype and you can say, right, I want to see objects that look like this. So you can see here these sources that best resemble this prototype. In this regime, you can see the difference between things that are sort of core-dominated morphologies versus more extended lobe-dominated morphologies, and you can kind of pick out the sources of interest. And like was shown earlier, if you want to, you can then say, right, I've got a new object. Where does this object belong? Or I've got an interest in this kind of object. Find me all the objects of interest. So as well as this, you can go and look at the outliers. So like we said earlier, you can say, right, find the objects that don't resemble anything in my map. And you can do this by just ranking by the Euclidean distance from your metric. And you get down to these kind of very weird and wonderful morphologies, and I'll just pick out one of scientific interest. So this is a small kind of radio relic within a emerging cluster or a cluster. And these are kind of rare and unique objects that LOFAR is particularly sensitive to. And if we want to go and find these in new data without having to scour through it with our eyes, this offers a really neat technique of just basically putting any new data we have through to pick out the interesting objects. So it's a way of visualizing and exploring this data. So I should go back to this. So you can see the URL at the bottom. You can have a little play yourself. This is fully public, so you can see what the code does and how we can mix with it. So this is just to illustrate what we're saying. If you just take the sources that have got the highest Euclidean distance from the best matching SOM, you can pick out things that, in this case, are obviously typically biased towards extended and kind of larger emission, but that's the things we're interested in. That's what we want to find from our data. So another challenge I'm going to talk about briefly to kind of illustrate where we're going in future is that part of the work we did for LOFAR DR1 was a lot of work was done by hand. So you run your source extraction catalog and you get these different Gaussian components or these different sources. But it's often hard to tell which of these radio sources are associated together because you might have some lobe of it, two different lobes of an AGN separated by some very significant distance. These could be arc minutes away. And there might be no visible flux between them. So you have to go through by hand, and we've done this with a kind of LOFAR galaxy zoo, but radio galaxies, you've done this before. Yeah, associate these individual components and join everything back together into the sources. And this is obviously, again, time-consuming, and we will be expanding this to a Galaxy Zoo 2 for our kind of DR2 to give us a few thousand square degrees. But after this, really don't be wasting human time doing something that's actually very simple. And this is where things like these faster region-based convolutional neural networks come in, where we can, using our training samples, get the neural network to basically identify our sources, localize them, and also classify them. So here they're just in a simple example of looking at how many peaks there are and how many components there are within that radio source. And that saves us potentially a lot of effort in terms of manually going through and joining things together. So we kind of go through these steps, and it cuts out a lot of the hard work that we've gone through. I think in future I can see that there's kind of a much broader picture we want to put these things into. So as we get onto the full sky survey for LOFAR with lots, but also in the next generation SKA surveys, we want to be maximizing the science we get from these data sets, but also minimizing the effort that goes into analyzing them. So we can come on to some sort of picture like this, where we've got an integrated source classification, identification, localization procedure using some sort of advanced CNN. Once we've found those sources and we want to explore them in more detail, we can then look at how we visualize and explore that data. So that's things like the SOMs I presented earlier, and also the TSNE, which kind of doesn't put things into a different shape. You can just find new patterns and find interesting things in a data space, in a kind of parameter space that we never explored before. And then that obviously allows us to kind of build much more intuitive services in the future. So when you go to your VO, you just want to kind of put in an SQL query and get out numbers. Maybe you want something a bit more interactive, or you want to say, you want to provide a source that you found, upload one of your radio sources and get the VO to give you back everything in the LOFAR data LOFAR survey that looks like your object without having to go through a lot of intermediate steps yourself. Because these data sets are going to be way too big to really analyze in detail, and we need to have a lot of help and a lot more intuitive systems to get through that. So I'll just leave it with my summary, and thank you for your time.
That's good. Nice talk. I'm just wondering, you're doing all of your analysis in the image plane.
Yeah.
Is there any scope for going back one step and doing things in the visibility plane?
I guess so, yeah. I mean, the code is pretty agnostic about what you give it, right? So we've given it just one radio image, but equally, you can give it multiple layers, you can give it optical, infrared, etc. as well, and you could give it visibility. I guess it's just a way of how you kind of capture that in the right size of vector. Because I imagine with something like interferometry, right, the scales you're looking at are very different, whereas when you put it at pixel scale, you're condensing a lot of information from very different UV scales into kind of the same physical pixel scale. So I don't know.
Sorry, can I ask about a LOFAR Zoo question?
Yeah.
So Radio Galaxy Zoo was about to combine the infrared and the radio.
Yeah.
So for LOFAR Zoo, which kind of infrared or optical data you are going to combine with?
Well, so actually the key step from the Radio Galaxy Zoo was joining the two sources before, right? It gave you contours to click on that said these two radio components are joined together. It gave you the infrared as a kind of reference point to help you judge that. And then they were joining that radio source afterwards. But the key kind of thing they needed from the humans was to join those two sources together. Because actually once you've got two lobes connected, you can look at kind of where the fluctuated centroid is, and that gives you a good position to start with. But if you don't know they're associated, you don't know. So yeah, it will match to whatever infrared optical data is available to answer your final question.
Thank you.